Hi, I'm Michael Hansen, and welcome to Mike's Observatory. Not so long ago, I watched a video by a guy called Dave. His channel is called Professor Dave Explains. And he showed with simple logic how he could completely destroy the flat earth idea using just the moon. And I thought to myself, I want to do the same thing, just with the sun. So let's get going. The challenge with using the sun as a reference instead of the moon like Dave did is that whereas the moon have distinct surface shapes that you can clearly see with the naked eye, so if we were to rotate the moon in a different angle, you would notice it. The sun doesn't have those distinct features unless you look at it from a telescope or using a telescope, because there you can see sunspots and protuberances and all things like that. So in order to do this, I do need to invoke some math. Some simple math. It's basic high school geometry. So any person who has intended, well, probably some people would even see these formulas used in elementary school, but anyone who has intended simple high school math should be able to follow. So let's get going. I want to start by setting the stage for where we are and why we are talking about this. Alright, so now you should be able to see my screen and you can see my mouse as I move it around. So let's start. So here are some examples of flat earth models, and this is actually the very first challenge that anyone who wants to deal with flat earth discussions or claims is that flat earthers don't tend to have one unified model that they use. They tend to disagree on most things actually. But I do think that many flat earthers tend to use this Samuel Rowbotham as their sort of guiding light or whatever you want to call it. This is the name that they usually tend to go to, but as you can see here, there are many different models that we can choose. For example, the convex earth, that is, well, it's, I want to try to keep an open mind for now. But one thing that they tend to agree on, all of them, is that they say that the sun is positioned above the earth. And so instead of the earth is revolving around the sun, it is the sun that is sort of rotating or going around above the earth at a certain altitude. So if we use the numbers that Samuel Rowbotham provided in his works, he states that the distance to the sun is roughly 3,000 miles, or in kilometers 4,828. The size of the sun should therefore be around 32 miles or 52 kilometers. And one thing that we do know is that every flat earther seems to agree that for somebody standing on the equator, because that is what we can observe, the sun should at a given point be directly above them in zenith. So we know we can use that relationship to figure out whether the flat earth model is viable or not. And therefore I have also included, this is not Samuel Rowbotham's numbers, but I have included them anyway, that the distance from the pole to the equator is 4,325 miles, or 6,920 kilometers. One of the main arguments that I'm going to go into is that flat earthers tend to use perspective as sort of a magical argument. It's become their stable ad hoc argument every time they seem to be stuck at a certain point where they can't explain what is going on. They either say perspective or fake or CGI or anything like that. But when it comes to the sun setting, they tend to use the perspective argument. And so in order to test that argument, we need to know the angular resolution of the eye. Now, the angular resolution of the eye is actually not a pretty easy number to find, because the angular resolution, or as we call it, the diffraction limit for any optic, is given distinctively for every frequency of light that we use. So green will have a different angular resolution limit than red, for example, even for the human eye. But the number that I could find that seems to be reasonable in this connection is 0.02 degrees. So whenever we have an object which angular size is 0.02 degrees or less, our eye will no longer be able to resolve that object. All right, let's go on. So I'm going to use basic geometry, but because I know that flat earthers tend to refute any kind of math because it is untested, it is unproven, blah blah blah, all that, I'm going to show that the formulas that I'm going to use in this example here works in real life. Now, my desk is placed in the living room, as you probably can see behind me. And for some reason, my children, I have 2 of those, tend to dispose variable kinds of toys on my desk. And yesterday was no exception for that. So I found this little Lego thingy that my daughter have constructed. I'm not really sure what it is. But I thought to myself yesterday, I can use that. I'm going to use that particular little thing to test this math here. So let's go on. So the basic geometry that we're going to use is these sinus, cosinus, and tangent rules. Now, in this particular case, I'm going to use the tangent rule because that is what we can use here. What we are interested in is finding the adjacent length by knowing the angular resolution, or the angle here, theta. And we know also the opposite, that would be the height of this little thing here. So we have the formula here. Tangent to theta is equal to the opposite length, or the opposite side, this one here, divided by the adjacent side, which is this one here. I hope that most flat earthers can agree on this formula here, but just to be sure, I'm going to test it out. So in order to figure out how to find, we wanted to know we wanted to know the adjacent. So in this case here, I've renamed it, so O is the opposite and A is the adjacent. So we have the same formula here. Tangent to theta is equal to the opposite divided by the adjacent. By flipping these numbers around, and you can do that if you want, you can simply just divide them by 1 if you want to. We get 1 over tangent to theta is equal to the adjacent over the opposite. And now that we have flipped them around, I call it that. It's not really what you do, but I call it that. You can now multiply by O on either side. So if we take this side first, we have A divided by O multiplied by O. We have O divided by O, it goes out. Here we have 1 over the tangent to theta times O, and that is the same as O divided by tangent to theta. So our new formula becomes the adjacent is equal to the opposite divided by the tangent to theta. This is the formula that we're going to use throughout this video. It's the only formula, almost I would say, that we're going to use, but it's only one that matters. So I took this little Lego thingy here and cleared our dinner table, or sorry, our living room table as much as I could. And as you can see here, the length, and I'm sorry I didn't convert it into inches, but I used my measured tape that I had, and I measured from the end of the table to that little Lego thingy to be almost 130 centimeters. And also I measured the height of this Lego thingy to be approximately 4 centimeters in height. Now, in order to alleviate any measurement errors that I have done, because you always make measurement errors. That's right, flat earthers. Whenever you make a measurement, whenever you take a picture, whenever you do anything to measure something, you have to include some kind of errors. So I have chosen to say, well, I think that my measurement is within plus minus half a centimeter. So the distance, which is the adjacent, is 130 plus minus 0.5 centimeters. And the height of this Lego thingy here is the opposite, which is 4 centimeters plus minus 0.5, that's half a centimeter. All right. So in order to measure the angular size, I use a little app for my phone that is called Theodolite. Now that app can do a heck of a lot of things. It can give you the exact position where you are at. It can give you the exact direction that you're looking at. It can give you all kinds of different. It can even show me that I'm approximately 8 meters above the surface of the earth. That is the water surface. But what it can also do is it can tell me what the angular size of an object is. So by doing that, and I can't show you exactly how I did it, because I can't take a picture of that exact moment. But what you do is that you point it to the bottom, press the AB here, and then select, well, in this case I selected the B. Then you move it up to the top, well, it's the top of the object that you want to measure. And then you press here again and say A. And as you can see here, I have A here and B here. So this is the height, the angular height at that distance from, of that object here. That is the angular size. Now by going into AB and say calc, and then check get the angular sizes, the angular differences instead, we can find that the angular size of this little thingy here is 1.8 degrees. Now the uncertainty in this program here is 0.1 degree. So there's also an uncertainty in here as well. So let's begin to calculate. We know that theta is 1.8 plus minus 0.1 degree. We know that the opposite, the O, is 4 centimeters plus minus half a centimeter. So we put in the numbers. A is equal to 4 centimeters divided by a tangent to 1.8 degrees, and we get 127 centimeters. Now our measurement was 130 centimeters plus minus 1/2. So 127 centimeters. Alright, my daughter just came in and wanted some help. What was it? Yes, we got 127 centimeters, but the measurement was 130. So clearly, if I was a flat earther and I stopped right there, I would say, well, it doesn't work. The formula, ha, I can see. Ha, there you have it. You globe earthers, it doesn't work. Ha, 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 ha. But that's a problem. And flat earthers say, oh, math doesn't work. But that's a problem. And that is the uncertainties. We have uncertainties of all our measurements. Now, and this is where it becomes a little bit cumbersome, and that is why flat earthers probably tend to run screaming away. In order to find the uncertainties for a formula like this, where we have basically, if we go back, we can say that we have, let me go here, we have, let's call this Q, then we have X divided by tangent to Y. So we have a division, but we also have a tangent. Those are both technically functions. So division is a function and tangent is a function. Now if we have a formula of several functions and we want to several variables and several functions, and we want to find the uncertainty, we need to use this formula here. Now, if flat earthers, if you haven't seen this formula before, it's completely okay. So what does it say? Well, it says that the uncertainty of A, that's the one that we calculated, is equal to the square root of, and these are partial derivatives. Usually use sort of a curly d, but I've used a big D here. So we take the partial derivative of A, that is the formula that we use, x over tangent to y, or whatever you want to do it. In this case, it is O divided by tangent to theta, as you can see here. We take that formula and differentiate it with respect to O, and then multiply that with the uncertainty of O squared, plus, again the same formula, differentiated with respect to theta, and then we time that or multiply that with the uncertainty of theta. And we can continue that depending on how many variables you have. You could put y, x, and c, and whatever you want to get in there. If we do all that, we get this formula here. Now it may seem like it's a terrible big formula, but if you check it out, it's actually not that bad. We have the uncertainty of O squared divided by the tangent to theta squared, plus O squared times or multiplied by 1 plus tangent to theta squared, parenthesis squared. So this entire part here is squared. That is squared, the tangent is squared, and that is entire part here is squared, times the uncertainty of theta squared divided by tangent to theta to the fourth. When we put in the numbers, we get, well, it's a half a centimeter, that is our uncertainty as on O. Theta is 1.8, so tangent to 1.8 squared plus O is 4, so 4 squared times 1 plus tangent to 1.8. As you can see, if you look at it, it's basically the same numbers that goes again. But the point is that we get our uncertainty here to be roughly 17 centimeters. So now we can compare these numbers. We can say, well, our measured uncertainty is 130 centimeters plus minus half a centimeter. Our calculated quantity is 127, but plus minus 17 centimeters. So when you apply uncertainties, you actually see that these numbers are reasonable, comparable. They work, it works out. So I have now shown you, flat earthers, 1, how you should always conduct your calculations. Use uncertainties. And 2, basic geometry works. Yes, let's go on. So the next thing we're going to talk about is how flat earthers tend to see the sun on the earth, over the earth. And the reason why I say tend to is again because they really can't agree on anything, apparently. This is what flat earthers can agree on, that we have sunsets, beautiful sunsets where the sun changes color and all that lovely stuff. And again, their favorite argument is perspective. So flat earthers tend to say, well, we have perspective, and that is the reason why the sun sets. So you don't actually see the sun go down below the horizon. You simply just see the sun go further and further and further away until it poof disappears. Right. Or is that so? That is what I'm going to show you here. That it doesn't work out. Let's check it out. Let's take a look. So the idea for flat earthers is that, like I showed before, the sun revolves around the earth. Now if we take the different seasons where the sun magically changes place, and if we also take the fact that you can see here that the sun's angular size doesn't change one bit in these two images here, not at all. But according to flat earthers, it should set because it changes angular size. There's a problem in that, right? Nevertheless, let's try again to keep an open mind and tend to one problem at the time. So for flat earthers, they tend to agree on, let's say in the summer period, at some point the sun should be revolving perfectly above the equator, and that means that any person standing here along this line here at the equator should be able to see the sun perfectly above him at one point in time. If we assume that we have an observer standing here exactly at the North Pole watching this sun right here, and we have some person here standing in the middle of Africa looking at the sun, we can roughly say that if we have the size of the sun, which Rowbotham have given us, which is O, we have this distance here, which is unknown to us, which is A, and we have the angular size here, which is theta. That has to work because we have just shown that this has to work. Now, flat earthers might argue that, well, the Rowbotham have given us the entire size of the sun, but you're only taking the half of the size. Yeah. That's true. That's perfectly correct. So what could I do? Well, I could say, well, then we take half of the 32 miles. That is roughly 16 something miles, right? 15 something. But then we also have to take, because the angular size of the sun is this entire sun here, and that is 0.2 degrees. So half of that would be 0.01 degrees. And you know what? It turns out that those two numbers, when you calculate it, are exactly the same. So it doesn't really matter. You can do it for yourself. Just take the 32 miles divided by 2, and then divide that by the tangent to 0.01. Remember, it has to be degrees, not radians, otherwise it won't work. But nevertheless, the number that we're interested in getting here is A. Also, I won't be using any uncertainties here, because even though I could put uncertainty on the angular resolution that I found on the sun, Rowbotham simply seemed to have pulled these numbers out of his buttocks, and therefore there are absolutely no kind of any sorts of uncertainty on those numbers. I would like to apologize for my poor drawing abilities. I have tried to make this as beautiful as I could in Photoshop using only my mouse. But let's go on. Let's try to figure out what A here is, this distance here. So again, we use the same formula that I did before, just like that. A is equal to O divided by tangent to theta. Our assumption here is, from what flat earthers tell us, is that the sun will vanish when theta is equal to or less or equal to 0.02 degrees. We also say that the size of the sun is what Rowbotham has given us is 32 miles. Now, I would like to state right now that if any flat earther out there is unhappy with what I've done here with these numbers here, please provide your own numbers and I will make the exact same calculation. I promise I will do that. I will even make a new video of it. But we put in the numbers that we have, 32 miles divided by the tangent to 0.02 degrees, and we get 91,673 miles. That is a pretty big number. But this is, like you see here, this is this distance here. But what we want to get is this distance down here, because that is where our little guy in Africa is standing and watching the sun directly above him. So let's go on. This is the system that we actually concerned with. We have just found A here. So we have our guy here at the North Pole. He's looking at the sun and it is about to set. So it should have a certain distance, right? He should be able to see it, right? At that time. Also, we know the height up to the sun, because again, this is what Rowbotham gave us. What we want to know is the actual distance. Now, in order for the flat earth to work, that distance cannot be anything other than the distance from the pole to the equator. Because otherwise this guy here standing at the equator would see the sun in a very different angle than directly above him, which he should be able to do. So, let's continue. By using the simple Pythagorean theorem, which is distance is equal to the square root of a squared minus height squared. I've used the same units that you can see here. It's simple. If you dispute this, then you have a huge problem, because Pythagorean theorem is something that has been tested and used numerous times and tend to work all the time, actually. You can even try it out for yourself on a piece of paper. Again, do the same that I did. If you know the height and you know the distance, you can find this distance here or whatever you want to do. So let's see at what distance the sun would be directly above the earth. The distance should be 4,325 miles. Our calculated distance is, well, we use the same formula that I showed before. The distance is equal to the square root of 91,673 miles. This is the number that we found from our previous calculation, which the formula that I showed works, squared, minus the height that Rowbotham gave us, the 3,000 miles, squared, gives us 91,624 miles. So, our guy in Africa, which is 4,325 miles away, is actually 91,624 miles away, because you can see the sun directly above him. Or he doesn't see the sun directly above him, he just sees something else. No, as you can see, it simply doesn't work out. I'm sorry, flat earthers. Whether you use the moon and simple logic, like Professor Dave did, or if you use a little bit more math, a little bit more geometry, and you try to calculate your way throughout this system here, you'll find extremely big inconsistencies between what you would expect from the observations that we have. We know that a person standing directly at the equator at some point can look up and see the sun be directly above him. We also know that some person standing at the surface of the pole, the North Pole, would see the sun set at some point. At some point he shouldn't be able to see the sun anymore, because that is also what we observe. We do actually observe the sun set at the North Pole, which is also strange. Nevertheless, we find that in order for that sun to set, because of perspective, when the sun becomes smaller than the angular resolution of the eye, that distance should be directly above Earth, not in line of sight, but directly above Earth. Should be 91,000 miles, 91,624 miles. So I would like to challenge you, flat earthers. Give me some numbers. Give me some explanation of the inconsistencies between this number here, which I hope that every flat earther can agree on, that a person standing at 4,325 miles away from the North Pole, or the pole, either of the poles, should be able to see the sun directly above him at some point, because that is where the equator is. But the real distance, if we take the arguments that flat earthers use, that is the perspective argument, where the sun should set, how far away it should be in order for that to happen, the sun should be 91,624 miles away. I challenge you, flat earthers, give me an explanation, give me some numbers, give me anything that you can tell me about these inconsistencies other than math is fake or CGI or anything like that. This is simple math. I have shown you how it works. You can test it yourself. It works every single time. So please, flat earthers, come and get me.